This lecture is part of an online course on rings and modules and will be about free modules mostly. So just quickly recall what a module is. So if we have a ring R, a module M is something acted on linearly by R. And there are several sorts of modules. We can have left modules where we have R acting on the left, so R and M goes to R times M. We can have right modules where we have M times R goes to M, and this time if we're given an element M and R, we have an element M times R in M. And we have two-sided modules where we can multiply M by R on the left or on the right, and these left and right actions have to commute, so R1M R2 must be equal to R1M R2, and we will be using the difference between left, right and two-sided modules a little bit later. So just to recall the basic examples of modules, abelian groups are just the same as modules over the integers. Vector spaces are just the same as modules over a field, and ideals are the same as submodules of the ring R. And we can have left ideals and right ideals and two-sided ideals, and these correspond to left, right and two-sided submodules. I won't define what submodules are because this is kind of obvious. There's also a way to switch between left and right modules. So if we have a ring R, we can define the opposite ring R op, which is the same as R except you reverse the multiplication. So you define the multiplication R1 times R2 in the opposite ring to be equal to R2 times R1 in the ring R. So for a commutative ring, the opposite ring is just the same as the ring R. And we can turn left modules over a ring R are sort of more or less the same as right modules over the opposite ring R op. And you sort of do this in the obvious way. If you try to define MR to be equal to RM, you need to switch the position of two elements of R. For instance, you want MRS to be equal to MRS, and for this to work, you see you need to switch the order of the multiplication of two elements to make M into a right module. Another thing you can do with rings is look at modules of homomorphisms. So we have the set of linear maps from M to N over the ring R. And now you've got to think a bit about whether M and R are left, right or two-sided modules. If M and N are left modules, or for that matter right modules, then you see that this acts on M and N on the right because you want RM F to be equal to RMF if F is in here. And if you look at it carefully, you see that this is not in general an R module. If you're used to working with commutative rings, this is an R module, so it's a bit disconcerting to find that for non-commutative rings this doesn't quite work. What happens is if M and N are two-sided modules, then Hom over R from M to N can be made into a two-sided module if you're careful. Here you have to think of M and N as being either left modules or right modules. Now for commutative rings, all modules are automatically two-sided modules, and this is sort of why for commutative rings this thing is an R module, because you can think of M and N as being two-sided. Well, the simplest sort of modules are free modules. These are modules that are just a sum of copies of R. So we may as well fix R to be a left module, for example, and then this will be a free left module. And a free module has a basis of elements in the usual way. So if the free module is M, it has a basis M1, M2 and so on, where M1 is 1, 0, 0, and M2 is 0, 1, 0, and so on. So it's pretty similar to vector spaces. For example, over a field, all modules are free modules. It's a basic property of vector spaces. Every vector space has a basis, which sort of means the vector space is just a sum of copies of K. Of course, for general rings, this is not true. For example, Z modulo 2Z is not free over the integers. So as soon as you move away from fields, modules get rather more complicated than free modules. What's the basic invariant of a vector space? Is they have a dimension. And this can be defined as follows. We just define the dimension of k to the n, sum of k copies of n, to be n, and we check in linear algebra that this is well defined. And we want to know, can we do the same for free modules over a ring? So let's try to define, well, it's usually called the rank rather than the dimension. So we're going to define the rank of R to the n to be equal to n. And the question is, is this well defined? So let's take a look. Well, first of all, yes, if R is a field. We just saw this, that you see in linear algebra, the dimension of a vector space is well defined. You also notice that it's no for stupid reasons in general if R is the zero ring, with just one element consisting of 0. And then any module is 0, so R to the m is equal to R to the n for any mn. And we see the rank isn't actually well defined because these two things are different. Well, apart from this rather stupid counterexample, all the obvious examples you can think of, the rank is well defined. For instance, the answer is yes if R is commutative, but R is not the zero ring. And this follows because R has a maximal ideal. We saw that any non-zero ring has a maximal ideal, so it has a maximal ideal, and then R over I is then a field. And if we've got a free module R to the n, we can just change this to R to the n over I times R to the n, which is a vector space over R over I. So we can read off the rank of this by just turning it into a vector space by reducing mod I. So for commutative rings, the only time this fails is for this rather stupid counterexample. We can also say that the rank is well defined if R is a finite dimensional vector space over a field, say. For instance, we could just take R to be, say, n by n matrices over a field K. And the reason for this is we can define the rank of R to the n by just sort of thinking of it as being a vector space over the field K. And we can see this is just a dimension over the field K of R to the n divided by the dimension over the field K of R. So most of the obvious rings you can think of that aren't zero have a well-defined rank for their free modules. Now let's have a non-trivial example So this is an example of a ring R not equal to the zero ring, where the rank of a free module is not well defined. And in fact, examples of this turn out to be quite common if you know where to look. So we're going to do it as follows. Pick any ring S which is not the zero ring. For instance, S could be Z or a field, say, if you want to be specific. And let's pick any module M over S with M being isomorphic to M plus M. And this is easy to achieve. We can just take M to be, we could, for example, take M to be a sum of infinitely many copies of S. And so on, and then M is obviously isomorphic to the sum of M with itself. And let's make this into a left module because, a right module, because at this point we have to be rather careful about whether our modules are left modules or right modules. And we're going to let R be the set of endomorphisms of M over the ring S. And this is going to act on M on the left, because we want it to commute with the right action by S. And let's have a look at what this looks like in some simple cases. For example, if M is the sum of copies, infinitely many copies of S, then R is more or less infinity by infinity matrices, except we've got to be a bit careful. It's not quite the infinity by infinity matrices. So if we write an element of M as tower S1, S2 and so on in M, where we notice that almost all Si are equal to 0. That means all but a finite number. Then if we want to multiply it by if we want an element of R to act on this, it looks like this. We have elements R11, R12 and so on, R21, so on. So these, the Rij are all going to be in S, and this acts on S1, S2 and so on. And you notice that in every column we must have almost all entries must be 0, because we want the action of this matrix on this vector to be another element of M, so almost all its entries must be 0. Notice that if we didn't have this condition that almost all the Si was 0 on M, so we try to take M to be a product of elements of S, then we couldn't define linear transformations by taking all matrices, because if you try applying this with an infinite number of entries there, you would find that you are getting a undefined infinite sum. I mean, you could try and restrict to having all but a finite number of entries in each row non-zero, and that would give you some linear transformations, but not necessarily all of them, so things get a bit complicated. So whenever you're looking at infinite matrices in algebra, you normally need some sort of finiteness condition on the rows or columns saying that most entries are 0. Notice if we put this finiteness condition on, then multiplication of matrices is now well defined, whereas if we had no finiteness condition, then multiplication wouldn't be well defined, because you would get lots of infinite sums. So anyway, we've got this ring R. So M is acted on the right by S and on the left by R, which is often this ring of matrices. And these right and left actions commute. And now we know that M is isomorphic to M plus M as right S modules. And now we can write the isomorphism between these in terms of linear transformations from M to itself. For instance, the map from M to the direct sum of two copies of M must take some element Z to AZ, CZ where A and C must be linear transformations of M. In other words, they're elements of R. On the other hand, the linear transformation back in the other direction must take some element xy in M squared to bx plus dy. Here again, B and D are now in R. So what we really have are two matrices. We've got a matrix BD acting on xy, and we've got another matrix AC giving the linear transformation in the other direction. And the composition of these two transformations in either direction must be is the identity. So BD times AC is equal to 1, and AC times BD is equal to the unit matrix again. And this gives us BA plus DC equals 1, and this gives us AB equals 1, AD equals 0, CB equals 0, CD equals 1. So we've found some elements A, B, C, D in our ring R with these properties. Notice, by the way, that we've actually got non-square matrices that have two-sided inverses. You may find this a bit disturbing if you remember from your linear algebra course that the only invertible matrices are square. Well, that's when you're working over fields or commutative rings that aren't zero. Over non-commutative rings, you can get examples of non-square matrices with two-sided inverses. Notice, by the way, that if the ring were commutative, then AB equals 1 would imply BA equals 1, and similarly this would imply DC equals 1. So if the ring is commutative, these imply 1 equals 0 if the ring is commutative. So this is something that can only happen in an interesting way for non-commutative rings. So we found a ring with 4 elements with these properties such that the ring is non-zero. It's this huge matrix ring. You could write A, B, and C and D as enormous matrices if you really wanted to, but there's not really much point. Now we notice that in a ring with such A, B, C, D, satisfying the relations above, if M is any M is any bimodule, that means R acts on the left and the right, then M is isomorphic to M plus M. And this follows just by using A, B, C, D to give an isomorphism between these on both directions. And this is not an isomorphism of bimodules, this is an isomorphism of right R modules. And this is very confusing because the elements A, B, C, D giving this isomorphism act on the left on these two, so they commute with the right action of R but not with the left action of R. So this is an isomorphism of right R modules but not an isomorphism of left R modules. And now we can just take M equals R, which is obviously acted on the left and the right by R, and we find that R is isomorphic to R plus R as a right R module. In particular, we see there's a free right module of rank 2 isomorphic to a free right module of rank 1. So the rank of a module is not well defined. This ring also has the property that 2 by 2 matrices, the ring of 2 by 2 matrices over R is actually isomorphic to the ring R itself. That sort of essentially follows from the fact that R plus R is isomorphic to R as a right module. This sort of construction used, sort of infinitely generated modules over our original ring S, and roughly speaking, these sorts of bizarre effects don't tend to occur if your ring is sufficiently small, and for instance it doesn't occur if the ring is finite dimensional over a field. But as soon as your rings get rather large, you can get really bizarre effects like sums of two copies of a module being isomorphic to a module. If you look at von Neumann algebras in analysis, the same sort of phenomenon occurs for type 3 von Neumann algebras. Again, the rank of a module is not terribly well defined. There's one particularly important property of a free module that I'll want to discuss, which is that if you have a surjective map of modules from B to C, and you've got a free module R to the n mapping to C, then you can lift this to a map from R to the n to B. And that's fairly obvious because you take each basis element, you take its image in C, and you lift that basis element to B, and that gives you a map from the free module to B. More generally, a module with this lifting property, that if you've got a map to C, then it lifts to a map to B, is called a projective module. Next lecture will be about some properties of projective modules and examples of projective modules that are not free.